Alright, hey there peeps! One of the coolest physics principles there is angular momentum. Alright, angular momentum. It's actually quite easy as well, but the ramifications are so cool, used in lots and lots of sports. So what is this angular momentum thing? Well, it's the rotational equivalent of linear momentum. Check it out. Angular momentum has the symbol L, and it is equal to I times omega. Rotational inertia times angular velocity. This makes sense because linear momentum is mass times velocity. Mass being linear inertia, right? Just the amount of mass will determine how much resistance to motion there is, but in the rotational world we know that it's I, so it's dependent on the distribution of mass as well as the quantity of mass. Omega is angular velocity, so it's the velocity again in radians per second around a circle. Okay, so let's take a look here. The units are kilogram meters squared over seconds. Where does that come from? Well, it comes from I, for example, being mr squared, but some variant of that perhaps. So that means we've got kilograms and radius squared, that's where the meter squared come from. And we've got, with omega, radians per second. So where do the radians go, you might ask, in the units here for angular momentum? It's because rads are not considered a true physical unit. So I don't know what that means when my name is Morad. Like, there's more of me, but then I don't know. Ah! It just means that it's a phantom unit. There's just more phantomness. I can dig with that. Certainly. Alright. So that's it really for angular momentum, but it really gets used when we consider the conservation of angular momentum. Alright? So, what does that mean? Over here, when there are no external torques that act on the system, because that would be a no-no for conservation stuff, we got L naught equals L final. That's it. The angular momentum that we begin with is the same as the angular momentum that we end with. It just gets rearranged. So let's take a look at an example of that. I'm kind of feeling that right now. There's a little angular momentum there. Example, you got a hoop. A hoop, you know, something like a hoop, or it's kind of a disc or a ring, a ring, where I equals mr squared. It actually does for that, all right? And the hoop is rotating and then doubles its radius. What happens to omega? So we can actually answer this question pretty easily here. So you can imagine that suddenly this object has a radius that's double. You're going to ask, where did the other material come from? Ugh. Well, okay. Remember that we have a situation too where point masses have the same rotational inertia as the hoop. So you can be holding like two weights, and if you then double your radius, so you're holding it out here and you double, like go out there, like see my hands, they go out like this. And so you're changing the distribution of mass that way, and effectively you are increasing the radius. So even if you're not a hoop, it still works for point masses, so objects in your hands could be like that too. So what we've got here is omega final, but if I solve for it, equals rotational inertia original times omega original over rotational inertia final. The change came in the distribution of mass. So here it is. We have mr squared for I naught, and for I final, it's m, and in parentheses 2r, we double the radius, squared. So remember that the 2 gets squared as well. The r's squareds cancel, the m's cancel, leaving us with omega final is actually equal to omega naught divided by 4. It's going to rotate 4 times slower, and so it's moving. The rotational frequency is 4 times slower, as well as the velocity itself, when knowing that omega is v over r. Okay? So that's an interesting thing. So really, who does this? Who does this thing? Well, figure skaters, for example, when they go into a spin in a pirouette, they can control that by distributing their own weight, their arms. So they can slow down by pulling their arms apart, and they could speed up by pulling in tighter. Okay, they change the distribution of mass and they start spinning really wildly fast. So that's a perfect example, and one that you've seen that totally works. So anything where there's rotation like that, where someone in sports can change their angular momentum, it will be to their advantage. So whether that's in football and if you make yourself tighter, you can then spin around somebody more easily. Gymnastics and other sports of the like. So that's what it is. Angular momentum, we're going to have some fun with it, and it's a really great concept, cool stuff, especially when we demonstrate it in the lab. All right, Morad. Phantom, out!